getting started. I passed out to everyone the registration for the Nebraska Academy of Sciences meeting that is on April 21. All you need to do is put in your name on the top line, your phone number, I don't know why they care about that, and your email address. And one more thing, if you plan on attending the Mybin Memorial Lecture, I don't even know what the topic of the Mybin Memorial Lecture is yet, but that's their big name speaker that they bring in. So it's usually pretty good. So if you plan on attending that, it's 11 o'clock, and just check it. No, we're not paying for lunch if you were thinking about that. But we will be paying the $15 registration fee, so that's why I'm having you fill them out, collecting them, and then send it with money to Nebraska Academy of Sciences. So make sure that you give those back to me so I can send them in and get you guys registered for this. I think it's a great experience for my students. That's why I talked to Carrie into doing it, since it was not in the budget for this year. Okay, any questions about filling that out? Nope. Okay, let's finish up relativity and start with the photoelectric effect. So we're starting with a clicker question. What happens to the total mass when an exothermic nuclear reaction, for instance, the decay of carbon-14 into nitrogen-14, which also produces an electron, occurs? This is the reaction that I used for my for instance. Okay. Just you, Jerry. All up to you. All right. So we had 5, 1, 13, 0. We had enough information. Everybody agreed with that. KT Dieter. Let's explain this to the masses. I didn't even mean to be so funny, but that's how we physicists roll, It's just funny guys. Go ahead, Katie.
I'm not certain, but I chose A because of conservation of energy, and I tried to add up from what I know from GENIS, but
okay.
That's my next one.
Okay, so she said A for conservation of energy. Now, conservation of energy is the key idea here. But according to Einstein, we have that rest energy is equal to mc squared. So if it's exothermic, if it's releasing energy, where'd that energy come from? It came from its rest energy. So the rest energy had to drop so that we could release kinetic energy. And if the rest energy drops, what does that mean with respect to the mass? It drops. So the correct answer was the total mass decreases so that we'll have conservation of energy. And of course, before Einstein came up with this, that would have been a crazy crackerhead idea because everybody thought mass was conserved, that it was a fundamental thing. We can't create or destroy matter. But Einstein said, yeah, we can. Matter is just a form of energy. So let's actually do the calculation. Later on, I have a slide that says the answer is 156 kiloelectron volts. So we know what our target is, but let's do the calculation for how much energy is released. So if we look at this relationship, this equation, notice I was specific here. It's nitrogen plus. What does it mean if it's nitrogen plus? That it's 1 electron short. Why would it be 1 electron short? We started with carbon. How many protons are in carbon? 6. There's 6 carbons, or 6 carbons in proton. There's 6 protons in carbon. So we started with 6 protons. If it's a neutral carbon atom, how many electrons should it have? 6. Now, we had something bizarre happen in the nucleus because the nucleus changed to nitrogen. How many protons does nitrogen have? 7. So if it was a neutral atom, it would have had 7 electrons. But it had 6 electrons orbiting it, and the nuclear decay is occurring exclusively in the nucleus. It's not affecting the electrons. And so we still have 6 electrons orbiting it. Now that leaves an interesting question, one that's not for today. Where did that electron come from? That electron was actually created in this decay. The decay destroyed a neutron, created an electron and a proton, and one little thing. See that thing that looks kind of like a V? That's not a V. That's the Greek letter nu, because it's a neutrino. Neutrinos are neutral, that's where the neut comes from, and they're tiny, that's where the eno comes from. And later on we'll talk about the origin of neutrinos. The bar over it means it's antimatter. So that's an anti-neutrino, and in fact, if you want to be really specific, you put an E there. It's the anti-electron neutrino, because there's electron, mu, and tau neutrinos. Although with the current theory, it's more, there's the low mass, the intermediate mass, and the high mass that are linear combinations. Anyway, so we have, if we count the electrons, we had 1 less electron than we need for a neutral nitrogen atom. Now I put here, the atomic mass unit is commonly used in atomic and nuclear physics. 1 atomic mass unit is 1.66 times 10 to the minus 27 kilograms. But since we can use energy units for mass, we can also say that 1 atomic mass unit is 931.48 mega electron volts per c squared. And that's a conversion that's very, very useful to us when we get into nuclear physics. So if I want to do my calculations here, my parent side has just a carbon-14, right? So that means that the energy of the parent is going to be the mass of the carbon-14 times c squared. Well, I gave the mass here in atomic mass units, so that's going to be 13.99950 atomic mass units multiplied by that conversion factor of 931.48 mega electron volts per c squared. That's the mass. And then what do I have to do to get energy? Energy is mass times c squared. So I put the c squared here, and you notice the c squareds are going to cancel. And so the energy of the parent, and I see you got out the phone, so I'll let you calculate it, 931.48 times 13.99950.
13,040.25. 13,040.
Okay. And the units, mega electron volts. Now, how many significant digits do I have in this number? I have 5 because this number here had 5 significant digits that I used. I had here 2, 4, 6, 7 significant digits in that number. You want to make sure when you get to the end of your problem, you didn't limit your significant digits by how many digits you had in your conversion factor. So pay attention to that. If in the end I find out, oh, I should have had more significant digits, I need to come back and change that conversion factor to one that is more precise. So that's the parent side. Now let's go to the daughter side. The daughter side had a nitrogen 14 plus an electron, plus the electron antineutrino. First rule, the neutrino's mass is so small, it wasn't even determined until I think it was like 1996 or something like that. And so for all intents and purposes, it's 0. The digits are way off the end of what we have for the other numbers. So we will make the approximation that the mass of this is approximately 0. Makes life easier. We don't have to count it. When I started teaching general physics in 1995, there was debate about, do neutrinos have mass or are they massless like photons? Okay, so then we just have the nitrogen 14 plus, so it's missing an electron, and an electron. Well, I, not being an idiot, will combine these and say the two together are equivalent to a neutral nitrogen 14. You have to account for all the mass. So I didn't have the mass of nitrogen 14 plus. I did have the mass of an electron, but I need to account for everything. So accounting for both nitrogen 14 plus and the electron is the same as the mass of the nitrogen 14. Now, once again, you might say, well, when I have an electron bound to the nitrogen, isn't that going to change the mass? The answer is yes, but once again, it's in such a small, tiny amount compared to the change in mass otherwise that we can ignore it. So it's an approximation. Nobody ever measures the change in mass when you add or remove. Nobody measures the difference in mass between a nucleus and one electron separate and a nucleus with that electron added to it because it's too tiny. And so that means the energy of the daughter is equal to the mass of nitrogen 14 c squared, which is, and this time I'll put the c squared out front, c squared times, and I get my number 13.999 234 times 931.48 MeV per c squared. So if I do this calculation, what do I get?
13,040.00 or 01.
So, we had an energy difference of 0.24 mega electron volts. Now, how did I need to worry about the number of digits in my conversion factor? It looks like I do in this case, right? Because I took the 6th and 7th digits for my difference. But the fact is, no. Because I could have combined this into one equation and said the energy released, which we usually just call Q, is equal to the mass of the parent minus the mass of the daughter times c squared, which would be equal to 13.99950 U minus 13.999234 U times c squared. C squared is hard to read. If you do the subtraction first, how many significant digits do you have after the subtraction? 2. You have 0.000266 U, with this here being your last significant digit, because I didn't have a digit here to correspond with the 4. So there's only 2 significant digits there. My 931.48 had 5. The limiting factor was the mass precision. So I don't have to go through and use a different conversion factor. People understand the significant digits issue I just went through? All right, because I don't want people to be confused like, I don't know, it still seems to me that it's the wrong number of significant digits. But here we can see what happened to the mass. It decreased, and that difference in mass gave us the energy released. And we had, whoa. Okay, can we do the calculation again? Because I'm pretty sure that's not actually the value that we're supposed to get. On the other hand, 227
Yes.
times 900 and some is going to be in the ballpark of what you said.
When you multiply it by U, you get 0.24777.
Yeah. So 0.25
Yeah.
is the best And so later on when it says 156, that doesn't match the numbers we had here. I'm not sure why, but we're going to run with it rather than sit here and try to figure out how, we didn't do the work wrong. Now, we've already shown this equation from last class period. Newton's second law still applies because our first postulate is the laws of physics are the same in all inertial reference frames. So the net force has to be dp dt. And notice we said that it's not ma, because ma was an approximation that does work in our classical world, but since momentum has an actual different definition in the relativistic world, we can't put it in. So how can we use this? Well, we can find kinetic energy from this equation. Because we know work, if we do it the algebra-based form, work is force dot delta x, right? And we know that the net work is equal to the change in kinetic energy. So we can calculate the change in kinetic energy by calculating the net work done. Now, of course, we have to really do this with calculus. And the calculus is not so simple. It looks simple here, 3 steps, but there are some steps missing. The step going from here to here is missing, as well as the step going from here to here. Neither of those are trivial steps. They're correct. I verified them last night. Of course, it was 11 o'clock last night. But we have the integral of force dot dx. There's a little trick here. Force is dp dt dot dx. We moved the dt from under the p to under the x. And then we have dp dot dx dt, which is dp dot v. Since p, momentum, is mv gamma, it's in the direction of v, so we can drop the vector sign and just multiply because they're always parallel. And so getting to vd and then, v times the derivative of momentum, so that thing in parentheses is momentum, that's fairly trivial. But then you actually have to take the derivative of gamma mv, which is non-trivial, to get that that's the same as gamma cubed mv dv. And then you have to take that integral, which again is non-trivial because there's a v inside of gamma, and you find that it's gamma mc squared. So the change in kinetic energy is the change in gamma mc squareds. Now this gives us kinetic energy to within an additive value, right? Because we have a difference for kinetic energy. If you added 5 to both sides, it wouldn't look any different. So it's the correct equation for kinetic energy to within an additive value. And Einstein determined that we should put an additive, or in this case, subtractive value of mc squared. And so that's our equation for kinetic energy. Gamma minus 1 mc squared. Does that make sense? You bet it does. What should the kinetic energy be if something is stationary? 0. So how much would I have to add to gamma mc squared to get kinetic energy 0 if the velocity is 0? What is gamma if velocity is 0? 1. And so I'd have 1 times mc squared. What do I have to add to get to 0? Negative mc squared. And so that's why we have that form. So kinetic energy is 0 if something's stationary. So given that kinetic energy is gamma minus 1 mc squared, Einstein said, well, this is not rocket science. We know that the total energy should be the kinetic energy plus the potential energy. He said, well, okay, we're talking rest energy is the only potential energy we're having in my problems. And so he just said, let's say that the total energy is equal to the kinetic energy plus the rest energy. And so that's equal to gamma minus 1 times mc squared plus mc squared was his equation for the rest energy. And what do we find for the total energy? This is actually a lot easier, isn't it? Total energy is gamma mc squared. Kinetic energy is gamma minus 1 mc squared. Rest energy is mc squared. It's all pretty simple. The mass is a constant. The mass doesn't change as you change reference frames. Believe it or not, when I was your age taking this class, my textbook said the mass changes. Physicists have changed the way they talk about things since then. We had mass increase as one of the things we had to learn. Now we learn mass stays the same in all reference frames. It's just changing the way you do the math, but it gives us something more consistent to work with. So that's our equation for the total energy. And there it's worked out. Conservation of energy, woohoo! Still works because laws of physics have to be the same in all reference frames. Now, I mentioned kinetic energy needs to be zero. That's why we have to have gamma minus 1 if something's stationary. But we also have the complementarity that says that my relativistic physics has to agree with classical physics in the classical physics realm. That is if my speed is less than 1/10 the speed of light, like let's say my speed is 100 meters per second, my relativistic equations had better give the same result as classical physics. And so how do we take this and evaluate it for a speed of 100 meters per second? If you put 100 meters per second into your calculator for gamma, what value are you going to get? You did this in a homework problem, didn't you? Pretty sure I signed one like a week ago. You'd have gamma equals 1 over square root of 1 minus 100 meters per second over 3 times 10 to the 8 meters per second quantity squared. 100 divided by 3 times 10 to the 8 is 3.33 times 10 to the 5? 3.33 times 10 to the 5 squared is, what was it? Well, I said -5, didn't I? I said +5. Yeah, -5. Thank you. So if I take 10 to the minus 5 squared, that's 10 to the minus 10. So I'm going to have somewhere around 10 to the minus 10 or 10 to the minus 9. What?
It's -7, not -5.
Minus 7?
Yeah.
Okay. Then that makes it smaller.
Yeah. So then you come out with squared is 1.1 repeating times 10 to the -13.
So it's 1 over the square root of 1 minus 1.1 repeating times 10 to the minus 13. And what do you get then for gamma?
1 on my calculator.
Try subtracting 1 and see what it gives you.
It just says 0.
Okay, so his calculator gives us exactly 1. Exactly 1 isn't the right answer. It's not exactly 1. It would have to be 0 speed to be exactly 1. But the calculator can't go that far. Our calculators have limited digits. And so what we have to do is find another way to find gamma. So how do we do that? We use the old Maclaurin series. An expansion around 0. This is actually called the binomial expansion. And I'm not going to go through the Maclaurin series. I put it here so you can read through it. If you've taken calculus, you've learned to do this at some level. I don't remember which calculus class actually. It's probably not in Calc 1, Calc 2. But using that, what we find is gamma is equal to 1 minus 1/2 of VC squared. So that means in the limit where we're going much less than the speed of light, our kinetic energy is equal to gamma minus 1 times mc squared, right? Well, the gamma is 1. Actually, it's minus and minus, so it's plus 1/2 v squared over c squared. So this right here is gamma. But 1 minus 1 is 0. Thank you. And thus, the kinetic energy is just equal to 1/2 v squared over c squared times mc squared. Cancel the c squareds. 1/2 mv squared. So our relativistic equation does exactly give us the classical equation for kinetic energy in the limit where the speed is much less than the speed of light. This binomial expansion is only valid if your speed divided by speed of light is much less than 1. So in the situation that you're much less than 1, non-relativistic, then it gives us the classical result. That's an important result. It seems trivial, but it's important because it gives us a reason to suspect this might be valid. And there's the last 2 steps I just did. Now, see, I said it releases 156 kiloelectron volts here, which is what I was remembering. Not sure why we got a different number, but the question here is simple enough. If we have that much energy in the electron, how fast is the electron traveling? What way can you think of for doing that? Kinetic energy is equal to 156 kiloelectron volts. How can I go from that to speed? What was that?
1/2 v squared.
No, because it's going to be relativistic speed.
Okay. So just 1 minus gamma minus 1 times mc squared.
Here's a quick way to determine if it's a relativistic speed or not. Compare this kinetic energy to the rest energy. If the kinetic energy is much less than the rest energy, then it'll be non-relativistic. But this here is like 1/4 of the rest energy. It's going to be relativistic. So there's a quick way of doing the work. So what were you saying?
It's gamma minus 1 mc squared.
Gamma minus 1 mc squared. Well, I know what mc squared is. That's the 511 kiloelectron volts. And so I can find this as kinetic energy divided by mc squared is equal to gamma minus 1. Add 1 to both sides. And I have gamma is equal to and that gives me gamma. Once I have gamma, then I can invert the gamma equation to find the speed. So that's one way of doing it. But there's another way that actually turns out to be simpler once you understand it. So the next page is going to have like 5 lines to give the explanation. We start with a new equation. The total energy is equal, the total energy squared is equal to the rest energy squared plus momentum times speed of light squared. Where does that come from? It's somewhat recognizable to the 252 students. That is our momentum energy invariant. So if we take that equation and we combine it with the definition that the total energy is the kinetic energy plus the rest energy. So the second line is showing the total energy and then squaring it so I can substitute it in. Then I have the rest energy squared on both sides so I can subtract it out. And then if I solve for momentum times the speed of light, I find the momentum times the speed of light is this square root term. Now, once you have that, you say, okay, I have the momentum. Momentum is gamma v times m. That's going to be a lot of work still. But we're not done. Because by definition, if I take PC and divide by the rest energy, PC is gamma mv. That's momentum right there. Let me not use black. There's momentum right there. Momentum times speed of light. Divided by the rest energy, gamma mc squared. We have a lot of things to cancel. The gammas cancel. Makes life easier. The m's cancel. One of the c's cancels, and I'm just left with the ratio of PC over the total energy, or the rest energy, is V over C. So that means my final result is the speed, and I'm going to actually leave it as V over C, so it's as a percentage of the speed of light. And then I just put in my numbers, so that's going to be equal to the square root of 156 kiloelectron volts squared plus 2 times 156 keV times 511 keV, all divided by 511 keV. That's the entire calculation necessary to find its speed. So are you working it out for me, Jordan? No. Saw you banging away and was hoping. It's not your job, Jonathan. I appreciate you doing it for us, but everyone would be equally entitled to participate. What is which number?
Instead of the last term there.
It's 511 kiloelectron volts.
I get 359.6.
That's, as Ralphie Wiggum would say, that's impossible.
Yeah, that's probably. Oh no, that's the top.
0.8389.
Yeah, same.
Okay. So the calculation turns out to not be very hard, a lot less work than it would be to do the inversion of gamma using this new relationship that is the invariant. And so I said in class on Wednesday, we have a different method that makes life a lot easier. When we talk about collisions between particles, or we talk about the decay of a particle, we use that equation to simplify our life. Okay, I think this is ending relativity. What is the rest mass of a photon? Okay, everyone has answered, and we had 1, 14, 3, and 1. Okay, Brandy, how do you feel? Confident, right?
Sure. I put B, just based off the fact that earlier you said photons don't have mass.
Okay, based on the fact that I said photons have no rest mass, you said that. And at this point, that's really all you have to go on. But that is, to the best of our understanding, light has no mass. But here's a really surprising corollary. Light does have energy. And, we have that rest energy equation of mc squared. Well, light is not at rest, right? It's traveling at the speed of light. And so its total energy should be gamma mc squared. Still doesn't quite make sense. Well, we're going to work into that in the next chapter. We're going to work on what is the energy of a photon, but using the equation that we just saw, this equation right here, we can define a momentum based on the energy of a photon. So we can define a photon has momentum times c is equal to, has no kinetic energy, but it has its and so momentum of photon must be mc, which is interesting, huh? There's no m there. So you better say, instead of mc, E naught over c. So there is an energy associated with a photon. That energy means it has momentum. And if it has momentum, that means it has the ability to deposit momentum, to make a force. So when light hits you, it should be able to make a force. Now, I have a Crookes radiometer in my office. It doesn't work. So I didn't bring it in here to show you a non-working one. If you want to see a working one, go to Richard Clark's office. He has a working one. It was designed to measure the momentum of light, because our relativity says that the light should have momentum. And so it's supposed to be an evacuated bowl, so you have no air in there. And then you have 4 little veins, one side painted black, one side painted silver. Now, if light hits the black side, what happens to the light? It's absorbed. That's the definition of black. If it hits the silver side, what happens? It reflects. So the theory here was, I shine light on this. The side where the light was reflected, the change in momentum for the light was 2 times the momentum of the light. Because it comes in, bounces back. So the change is, P final minus P initial, which is the opposite direction, so it's 2P initial. Whereas if it hits the black one, the change in momentum of the light is just 1P initial. So you have a bigger change in momentum when light hits one side than the other, which means that you should have a bigger force on one side than the other. And so it should be propelled and go around in the direction away from the silvered side. Does that make sense? Made sense to scientists, so they made the tube. And they shone light on it. And it spun the wrong stinking direction. And so they're like, where were we wrong? And I don't remember, I think it was James Clerk Maxwell, but it could have been somebody else, and I hate to disparage somebody without knowing the name for sure. But some famous physicist wrote a paper to describe it, and he said, well, the black side's getting hotter. And there was some air in there because we're not able to completely evacuate. So when air came and hit the hotter side, the air rebounded faster. And that was a bigger force than the light's change in momentum. And that's what made it rotate. So he published this. Big man. Until people realized, no, because what's going to happen to that air molecule that bounced off the black side? It's going to bounce around, and you're going to very quickly reach an equilibrium where it's hitting the silver side, and you have a net change in momentum of 0. And so people realized he was wrong. Somebody else, and I don't remember the name again, wrote a paper describing the correct effect, which was actually air moving across the side of the vein that was causing it to occur. It was sent to the famous physicist who wrote the wrong paper to review it, because in science, when you write a paper, they send it out for peer review, for other people to comment on it. And if they say this is wrong, it doesn't get published. And so this guy was sent the paper that shows where he was wrong, and he sat on it. He just never returned it. So it didn't get published. The person who wrote the paper died, and then he submitted it with his own name. Yeah, that's fraud, right? It's an interesting story. It's good that I can't remember the names. But I don't have that device to show you because mine's broken. I mean, I can bring one in, but it doesn't work. So I have another one at home that I need to bring in. Donate it. Let's not do one more problem and just get to the end of this. How do you know if you need to use relativity? These are all the same rule. They're all based on the same idea. If the speed is much, much less than the speed of light, and for this we put the limitation pretty simple. If it's much, much less, usually means like less than 100. We'll just use less than 1/10. If it's less than 1/10 the speed of light, don't need relativity. Or if gamma minus 1 is much less than 1. As you saw when Jonathan tried to put 100 meters per second in, he got equal to 1. So gamma minus 1 would have been 0. If the kinetic energy is a lot less than the rest energy, that was the one that I used in talking to Jonathan just a few moments ago, or if the momentum is much less than MC. Those are all rules you can use to make a quick judgment. Do I need to use relativistic equations, or can I use classical? If you use relativistic equations, you'll be right. But we prefer to use classical when we can because they're easier calculations. So I suppose if in doubt, use the relativistic equation, but save yourself some pain and evaluate, do I need to use the relativistic equation or not? That's wisdom. All right, new material. The photoelectric effect. This is what Einstein got his Nobel Prize for. So what is the photoelectric effect? The photoelectric effect this picture looked a lot better. The photoelectric effect, well, let's see if I have a better picture. I have descriptions of quantum before I get to what photoelectric effect is. So let's talk about quantum physics. What do you know, Jerry, about quantum physics? Huh? I still can't hear you. He's learning now. Okay, learning now. Anybody have any conceptions of quantum physics? Jordan?
Basically, it's the idea that something can be in two places at the same time.
Okay. Something that we have in quantum physics is the idea that something can be in two states at the same time. He said two places. That is an example of it.
Isn't it like a focus on like really microscopic aspects of physics, like pieces of the atom?
Okay, a focus on microscopic aspects. A lot of people say that technically that's not it, but in practice it is. So it's not a nonsensical thing, but it's not technical either. Aaron?
The ideas of electrons having quantized energy levels.
Okay, the idea that electrons have quantized energy levels, which is what's going to be on the next slide. That's kind of where we start with the understanding of quantum physics. The basis of quantum physics starts with having only specific values available, quantized levels. And so an example of a quantized value is the charge something has. You can have the charge of 0, the charge of +1 electron, -1 electron, but you can't have a charge that's 0.265 charge of electron. So quantized means at its base that you have specific energy levels available. So the salient feature here is we're dealing with the specific levels. I thought it was on that first one, but apparently it didn't use the electrons as an example. An example we've already seen of quantized levels are the energies of a simple harmonic oscillator. When we have a wave on a spring, there's only certain, I said energies, I should have said frequencies. I said energies because if we're talking about light, that would have been correct. When we have waves on a string, there are only certain frequencies that would resonate. I could drive it with other frequencies, but they don't resonate. They're not going to have big waves. But only if I have the right frequency would it resonate. So we had a simple condition for a wave on a string that the frequency it could resonate at was an integer multiple of its fundamental frequency. So that's an example of quantization. The frequencies or wavelengths for resonance are quantized. When you describe quantum physics like that, it seems like it's going to be easy. It's not. Don't get the wrong impression. But it seems like it's going to be easy because you're dealing with something that's a pretty basic idea. So let's just check to make sure we understood what I just said. What does it mean if a quantity is quantized? So I was more specific here than just saying, what does quantum theory mean? Okay. We have 1, 3, 15. Okay, I'm a little disturbed.
That's not right.
I'm still a little concerned, just not as much. I tried to be very clear that this was not correct. It is a practical outcome that occurs in quantum physics, but it's not that the quantity is small. It's not that we're dealing with a small object. We generally apply quantum physics to small objects because just like with relativity, we generally apply relativity only when things are going really fast. We generally apply quantum only when we have tiny particles. But that's not what it means to be dealing with quantum physics. And here I said if a quantity is quantized, the quantity being quantized is not a statement about the object. And so those were wrong. I thought I had made that clear, but it is important to know it means the quantity can only have discrete values, like I used the example of the charge of an electron, or the charge of anything. Now, how does Einstein get into this equation? It starts with black body radiation. You recall when I had the lamp out here, we started with it relatively cool and it had an orange color. And as it got hotter, its color became whiter. And if I would have been able to get it even hotter, it would have become bluish in color. And so that's called black body radiation. The radiation something gives off just because it's hot. And we have some laws that dealt with that. We have Wien's law. That says the wavelength that has the strongest emission is equal to a constant, I think that's 2.9 times 10 to the 6th nanometers times Kelvin, divided by the temperature. A simple relationship between the peak wavelength and the temperature. And then we have Rayleigh and Jeans, this dude here, Jean, who came up with a theory based on physics to describe what the shape of how intense light is as a function of wavelength should look like. And they did, as far as physics could tell, a perfect job. Their math was impeccable. No stone unturned. And yet, you can see that doesn't look like the data. Not at all. If you're out in the long wavelength range, then it's a really good fit. But as you get to shorter wavelengths, it diverges incredibly. And so this was termed the ultraviolet catastrophe, because the perfect physics work done by Rayleigh and Jeans said that no matter what the temperature of an object is, it's going to give off an infinite amount of ultraviolet radiation. Which makes no sense. How do you give off an infinite amount of ultraviolet radiation? You have to have an infinite amount of energy that you're expending each second. That doesn't make any sense at all. So it's a catastrophe because it was a catastrophic breakdown of physics. And so people are working willy-nilly trying to figure this out. Enter, not Sandman. My wife would get angry that I even said those words. Good old Max Planck, I had heard that he got a telegram. The story I was reading yesterday said he actually had Rubens over for supper, and Rubens told him the sad news that at low temperatures, Wien actually did also work to try to explain that black body curve, that Wien's equation failed at low temperatures, so Wien was wrong. And over supper, they talked about it. After that guy left, he sat, thought about it. And before he had tea that evening, before going to bed, he had an epiphany. And he scratched out a postcard that very night to Rubens and said, well, if that's the case, then this equation, and he scratches out an equation, must be the right equation to give the shape of the black body curve, of the radiation curve that we saw right there. And he was right. Now, when I see something like that, I think, genius, right? Just by getting one piece of information to add to how this curve varied when you get out to high temperatures, he was able to come up with the right equation. Only one problem. You're in physics class. If you get the right answer for a question, how much credit do you get for that? 1 out of 10. We're in physics here. Planck just got the right answer. Why? Yeah, pretty much he guessed. He used his intuition. And so he's like, I'm a failure here. I've got the right equation, but no reason for it. I'm never going to pass with this. And so he sat down, and for the next couple months, he worked on what's going on here. And so 2 months later, he published an article that said, I can give a physics reason why my equation is correct if you allow that light is quantized. That light only comes in specific amounts of energy. That is, for a given frequency, I can have the frequency multiplied by a constant, or 2 times that, or 3 times that. So his equation was the energy for the light is HF. where h is the self-named Planck's constant, and f is the frequency. Now, he didn't believe this was true necessarily. He said, if it's true, then I can give you a physics reason I'm correct. And it was Albert Einstein who said, he's got a point. Light behaves as a particle, and that particle has an energy of hf. And so you could be hit by 1 particle, or 2 particles, or 3 particles, but not 1.657 particles. And we'll pick up with that next class period. We'll do an experiment on this in the lab. It is by far our most expensive experiment, so I warn you now, please be very careful with the equipment.